t-tests, ANOVAs, and other types of tests that are used in comparing continuous variables across populations. Is that correct? And if someone can just confirm to me that you can see my screen, that will be helpful as well. Can anyone see my screen?
Yes, you can see your screen.
Okay.
Yes, sir.
Okay. So we're going to start with the one sample t-test. Can anyone remind me what we use one sample t-test for? From your class, any volunteers?
Okay, to compare the mean of a sample to some known value.
Okay,
or
that
standard.
is correct. So you might be asking about, and who just answered that question? Can you give us a practical example of where you'd apply this in public health or in a hospital? No, that's fine. Okay.
For example.
Yes.
For example, if the mean of the population is a certain number, then one might hypothesize that maybe the current sample or population is below or above that. So they can do the one sample t-test to test that hypothesis.
Okay, thank you for that answer. So, like, what's your name, please? So when you unmute, just say your name and then speak, because I can't see when I'm sharing my screen, I can't see your names.
Okay, Tabise.
Sorry?
I'm Tabise, Tabi.
Okay, thanks for answering the question. So another example of where you would use a one sample t-test, for example, is if you are testing maybe a new medication for blood pressure, and you already know that the current standard gives you a 5 millimeter of mercury drop in your patient's BP on average. So your hypothesis would be that you can either say that the new test is not any different from the new medication, rather is not any different from the current standard, or you can hypothesize that it's better or worse, depending on how you state your null hypothesis. So I'll just go ahead. We're using the resident doctors data set. I've just downloaded the data set, so I will extract. Yes, okay. So I have SPSS open. And let me close that. To import data. My data is in CSV. Desktop. Starts 101 data sets. Resident doctors. Okay. It does take some time. I'm sure you've also experienced similar. Okay, so we can see the data set now. This is the data view. This is the variable view. And our intention is to do one sample t-test. So our resident doctor data set, we are just trying to see if the mean age of the resident doctors is significantly different from 30 years. So our null hypothesis would be that there is no difference between the sample mean and this mean of 30 years. Maybe the 30 years is the I don't know, the average age of resident doctors elsewhere in the country or in all other parts of the country. And we want to see if our mean from this resident doctors data set is different from the population mean. So we go to SPSS and we go to analyze. If you can't see me, or if you can't see what I'm doing, or if I'm moving too fast, please let me know. So we go to analyze, we go to compare means, and then we come here, one sample t-test. So that's the beauty of SPSS. It's very straightforward. You just point and click. I don't have to memorize any code. I'm sure Dr. Abioye gave us in the first lesson the differences between SPSS and R. So our variable of interest is the age, and if you see here, all the variables are on the left initially, and when you click on your variable of interest, you know, this ruler here shows you that this is a continuous variable. I'm sure you did intro to SPSS in one of the labs. So you just click on this arrow and it puts it in this box here. And this box shows you that this is the variable that you are testing. So our test value is 30 because we are trying to compare our sample mean to the population mean of 30. And then when you come here, there are a few options that you can decide to play with. For example, if your protocol says that you are doing conducting all your hypothesis testing to a 95% confidence interval, then you would leave it like this. But if you are looking for something at a different level, like 97 or 99%, then you would adjust it at this stage. Then here it gives you options on what to do with missing values. I'm not going to change anything here. That's not our topic of discussion for today. So once you are done with all that, you just click OK. And then, like magic, your results are out. So you have a table here that says one sample T statistics. And then here you have the the one sample t-test. So this is the table of interest to us. The statistic here just tells you that this is the number of observations in your data set, or rather the number of observations that were used in calculating this. Someone is unmuted. Are you asking a question?
Yes, please. Can you please zoom a little bit so that we can see it clearly?
Okay, let me see if is it possible to zoom this. Is it the output table that you want me to zoom, right? The this window, you want me to zoom it in?
Yeah, the entire screen.
Okay, is this better? Is it better? Or is you are still having difficulties?
Yes, they look so tiny that we cannot see what exactly the numbers are.
Okay. How about now?
Right. So now it looks a little bit viewable.
Okay. So let me go back to the data set. So I take it that you did not see what I was doing when I did the analysis. So just going back here, what we're trying to do is to compare the mean of this data set, of this resident doctors data set, the mean age in this data set, to a hypothetical test value of 30 years. So that is why we have come into this. This is the resident doctors data set, which I imported a few minutes ago. And then because we have only one sample, which is the sample of resident doctors, we have only one set of values for age, and we are comparing it to a test value. We are doing one sample t-test. So when you want to do that, you come to this ribbon up here and you select analyze, and then you come and say compare means, because t-tests and ANOVAs, they all compare means. And then we come to the one sample t-test. Now, on this left box, you have all the variables available for selection. And then on this right box, you have the variables that have already been selected for analysis. When you look at the icons next to each of the variables, you find there are some pictures on next to age, mental health score, and some other variables. You have a ruler to show you that these are continuous variables that are measured on a scale. While these ones with different colors, red, green, and blue, just like a category, they are showing you that they are categorical variables. So we are trying to do a one sample t-test. This is only applicable to continuous variables. Our variable of interest in this case is age. So we click this arrow and it takes it to the right. And then we go into the options box and we select all those options that I talked about the last time I did this. And then we come here to this box to input our test value. If you remember from the question here, we are asked to see if the mean age of resident doctors in this data set is significantly different from 30 years. And that is the reason why we have put in a test value of 30 here. So once that is all okay, then we just click OK. So can we see the output window now? Is it big enough? Yes?
Yes, we can see it now. Looks much clearer.
Okay. All right. So this one sample statistic tells us that we have 161 variables in this data set that were considered for the for this analysis, and then the mean and standard deviation are given here, as well as the standard error of mean. So in case you want to report the mean and standard deviation for age in this data set, you can also get it from here, although I'm sure you must have seen other ways of getting mean and standard deviation in SPSS. Now, coming to the actual output of the one sample t-test, you can see that it is showing you at the top, very top here, that your test value is 30. You are trying to test whether the age in this data set is significantly different from 30. And then the t statistic is 10.622. If you remember in class, they must have told you how to calculate the t statistic, but that is not, nobody calculates that by hand anymore. But then this is the t statistic. If you input that formula that was shown to you in class, you'd be able to get something close to this number. And then this is the degree of freedom. So our significance, that is the p-value, is, it shows that p is less than 0.001. So it's very, very small. If you remember, we used a confidence level of 95%, meaning that any p-value less than 0.05 is significant. That's our, that is what we have stated from beginning. So this, with this p-value of less than 0.001, if you actually double click, you see, you can see the, sorry. If you click, you can see the actual value of the p-value. So this is 2.7931 times 10 to the minus 20. That would be very difficult to represent in a table here. It's several zeros before the before you have any significant figure, and that's why it's represented like this, less than 0.001. So this p-value is less than our set significant level. Therefore, we are able to reject the null hypothesis. If we remember, our null hypothesis was that there was no difference between this test value this test value of 30 years and the mean age of resident doctors in our data set, which is 34.1. So given that our null hypothesis is rejected, then that means these two means are not the same. Have I been talking too fast, or have I managed to confuse anybody? Or is it clear and we can proceed to the next example?
Sorry, my question is, I have two questions. Sorry, why does it say two-tailed up there? And then if you can just explain.
Yes,
so I wanted to just go
so these two tails.
Okay.
These two tails means that you are just trying to check if there is a difference between the sample mean and the test value. You are not, your hypothesis does not say that the mean age of the resident doctors in this data set is greater than or is less than. Does that make sense?
Yeah, it makes sense. So is there anything?
Yeah, your hypothesis is just testing for a difference. It's not testing for whether one is bigger than the other in any direction. So it's not saying that your null hypothesis is not saying that the resident doctor's mean is greater than 30. Neither is it saying that the resident doctor's mean is less than 30. Therefore, it can go in either direction, and that's why it's two-tailed.
Okay, sir. Okay, sir. So my next question will be, is there anything we will do in SPSS if we are directional about our hypothesis? Whether I want to say it is less than or greater than, is there anything we will do that will change the statistic?
I am sure that is quite possible. I've not tried that before, but we can go into the means table. So when we come here, if you can see, I came to analyze and then compare means. So I came to means. So this is where you come when you want a bit more control over what you are checking for. So I'm sure if you come in here and check for a lot of the different settings, you will be able to find a one-tail hypothesis, but I do not remember how it is done at this moment.
Oh, okay, sir. Then lastly, the confidence interval from the table. How does it apply here?
Yes.
And there's a table
okay.
down there.
Thanks. Yes, thanks for that question. So coming back, so if you look at this confidence interval, the lower confidence interval is 3.36, while the upper is 4.89. Now, the way you interpret your confidence interval depends on what you are measuring. So for this particular instance, we are measuring mean, which is basically addition and subtraction, right? So the null value when you are adding or subtracting is 0. Does that make sense?
Not really.
Hello, who has the question? Okay. When you add or subtract, what if you say a plus 0, what does it give you? It still gives you a, right?
Yes.
And if you say a minus 0, it still gives you a.
Yes.
So it means that in a linear scale, when you are adding or subtracting, the null value is 0. The only thing that you can add or subtract to something to not make any form of difference is 0. Does that make sense so far?
Yes, that makes sense.
Yes. So because of that, when you are interpreting your confidence intervals, you would check to see whether your lower and upper confidence intervals cross zero. That is when you are looking at means, standard deviations, and things like that. However, if you are looking at something like a ratio, for example, an odds ratio or a risk ratio, because that is a ratio, you are dividing something by the other. In that particular case, the null value would be 1, because if you divide something by 1, it remains 1. If you multiply it by 1, it remains 1. So that is now the value that has no effect on a number. And then you'll be looking to see if between your lower and upper bands, there is the value of 1. Let me see if I can open a sketch. You see paint. So, yeah. So this is a number line, right? And then our, let's say, this is 0, 1, 2, this is 3, this is 4, this is 5. Here we have 0. And where's our confidence interval? It's between 3.36 and 4.89. So when we come to the number line, where is it? Our, let's say 3.36. Let's use another color. Let's say 3.36 is here. So this is the lower band of our confidence interval. And then the upper band is 4.89. So let's say it is here. So this is the interval. Confidence interval is here. So it doesn't cross 0. So if your p-value, so basically you can either report, when you are reporting your statistics, you can either report p-value or confidence interval, because like we have seen in the p-value is much less than 0.05, which means it is significant by our own definition. And our confidence interval also is confidence interval does not cross 0, which means that it is also significant. So regardless of how you check it, if you check it using confidence interval, what it gives you, if it is significant here, it will be significant in the p-value. If it is not significant here, meaning that your confidence interval, let's say it starts from somewhere here and it ends here or wherever, as long as you have 0 as part of that confidence interval, then it is not statistically significant. Does that make sense?
Yeah. I was trying to understand how it relates to the mean that we just calculated. That's right.
Okay. All right. So that was our first example for the one sample t-test. Page down. And then, as you can see,
I have a question.
Yes.
Sorry. Yeah. So does that mean the p-value is the only value that we have to consider to draw a conclusion here? I'm just wondering what does the t statistics tell us? If it's 10, what does it mean? Like in this case,
the t statistic does not really mean anything. The t statistic is what you have calculated. Let's I don't remember the formula for calculating t statistic. You get it from, I think you do some subtractions and then you do some divisions. But way back when we used to do our statistics by hand, you would actually take this t statistic and go onto a 4-figure table where you have several values for one sample t-test, and then you would go under 10, and then you would trace all these three decimal points, and then you would also use this degree of freedom would also come into play, and you would check across that row and column, and at that point using the significance value as well. You would basically be tracing across that four-figure table to get whether your p-value is statistically significant or not. Sorry, you would use that to go into the four-figure table to get what your p-value is for this t statistics at this degree of freedom. But we are doing all of this in the computer now. The only thing I had to do was to click one sample t-test and everything came out. So in terms of reporting, people usually don't report the t statistic. They would report that they did a t-test, whether one sample or paired sample t-test. But yeah, as far as I know, that's the use of the t statistic.
Sorry, thank you, sir. I think this clarifies. I was mistaking the t statistics for the mean of the age, but I've just seen the difference mean. And you
This
can
is
see
the
that
mean
the
here.
difference mean is contained within the confidence interval. So if we calculated the difference mean and then our known mean fell within this confidence interval, then we would say that there is no statistical difference. Am I correct?
Can you ask your question again?
So I'm saying that I had mistaken the t statistic for the difference mean. So under the one
Yes.
sample test, I can see the difference mean is 4.1. And
Yes,
that
because
4.1
you
actually
subtracted 30 from here. Yeah.
Yeah, so the 4.1, the confidence interval is the interval lower and upper bound around that difference mean, right?
Yes.
So let's say
Yes.
that if, for instance, our known mean age that we used to calculate this was now 4.5, it will fall, if it was not 30, rather it was 4.5, it will fall within this confidence interval, meaning that since it's within the interval of the difference mean, then we will say that the mean age and the new one we just calculated are not statistically, there's no statistical difference between them. Is that correct?
No, because if you used a mean age of 4 point something, then your mean difference will be different. This mean difference gives you is the difference between this 34.1 and 30. If you use a test value of 4.5, this would change. So this confidence interval is the confidence interval around this mean difference. So what you just need to understand is that for a mean, if this value contains 0, then it's not statistically significant. If it does not contain 0, as in this case, like if this 3.36 was minus, then before you get from minus 3.36 to 4.89, you would cross 0. So if this was minus, then your mean difference would be statistically insignificant, which means there's no statistically significant difference between the two means.
Thank you very much.
Okay, so can we see that the output here is similar to the output that we have on here? 3.36, 4.89.
It's similar to the output we have where? On the
So
presentation.
this is the output from the presentation, 3.36, 4.89. So now we have found out that the sorry?
The screen is not visible.
Okay, let me go back. Can we see now?
Yes, we can see.
Okay, so we have now determined that the average age of the resident doctors is significantly different from 30. How do we interpret this? How do we report this in a paper? The person that asked the question about mean difference has already taken a step towards the answer. So that would be, you would say that on average, the average age of the resident doctors in this data set was about 4.1 years higher than 30, with a confidence interval of 3.36 to 4.89. Does that make sense?
Yeah.
Okay. So
sorry, the table below doesn't mean anything. The effect size, Cohen and Edge. What?
It does. It's not very. It's a bit less intuitive than even this table. So we are sticking to explaining things that are very easy to explain. Now, if you have interest in like effect sizes and all that, you can easily read about them or watch videos about them. Okay, so I'm going to the paired sample t-tests. In paired samples, you use this to examine the difference between paired observations. Like in this case, the systolic blood pressure at week 1 and week 2. So it means that you have measured the systolic blood pressure for the same set of people, and then you are comparing the mean systolic blood pressure at week 1 versus the mean systolic blood pressure at week 2. Does that make sense? So you are basically asking yourself, has the average blood pressure changed within 1 week, within the past week? That's basically the question that this is answering. So again, your null hypothesis, can anyone volunteer a null hypothesis for this question? Whose mic is unmuted?
Yeah, I have a question. So my I don't know if you can walk me through. I opened the SPSS app. I'm trying to import the file, but it's the file was in PDF. I don't know if you can walk me through so that I can do like what you.
Are you saying you are unable to import the data set?
Like the data set that we got from the classroom is in PDF file. So I as in my SPSS lab is open. I'm having some issues. I don't know if you can walk me through.
Okay, let me see. It's
in PDF.
So
it's not Excel. It's in PDF.
So if you can you see my screen?
Yeah, I can see.
So you have to scroll down to where it says data sets.
Oh, okay.
And then you'll be able to see, for example, this is the resident doctor CSV, and then some of the other data sets are also listed here. And I think even in the items that were posted, you would find, in addition to the videos that were posted ahead of time, they also posted a data set or a link to the data set. So the
data set, the data like the SPSS lab. So the one I saw from the group is the SPSS lab 4. Lab 4 and then lab 3, something like that. So, but they are in PDF. That's the thing. So
units.
They're in PDF. SPSS lab 2.
Does anyone else have this problem?
SPSS lab 2 is in PDF. That's what I'm saying. Like, I don't know.
Okay. Does anyone else have this problem? I'm just
I have
throwing
a
it out to the
similar
house.
problem, not exactly the same, but
Mhm.
somewhat similar. So the data sets, I have been unable to download the ones that are on OneDrive. I am not sure why. I sign in with my OneDrive and then it's not, giving me access. So I don't know if it's possible to put them all on Google Drive, because the two that were shared via Google Drive, I was able to download.
So
That's
my
the problem.
question now is that so my question now is, if it's on PDF, how do we upload it into the SPSS? Like the SPSS lab 2 now, they put
Yes.
on this thing. How do I put it into my SPSS with PDF as is on PDF? That's what I want to know.
I don't think SPSS has the capacity to take PDF data from PDF files. I'm
So
doing
how do
an
we do
upload
that?
right now.
Okay.
Give me a second. I'm uploading. I'm doing an upload right now.
Okay.
I've just made an upload of a zip file containing SPSS data sets. So anyone who has issues downloading should be able to download.
So this one is going to be on Excel, right? The one you're uploading.
Yes, these are CSVs or SPSS files.
So those lab 2 PDF, we don't need to, those ones that are in PDF, we don't need to, it's the same
The
thing, like the
PDF
ones
is
you're,
what I'm presenting.
oh, okay.
What I'm
okay.
presenting here with the questions and answers is the PDF. So it's not a data set.
Okay. Looks like, so, okay, if the PDF is not the data set, so which ones are the data set? So that's not the data set, okay.
So what I have just uploaded here is the data set.
Okay.
Oh, am I sharing my screen? I'm not. Sorry, Chef.
No.
I think resident doctors and heights, those are the only data sets so far, right? I don't know if, make sure we're on the same page. The resident doctors and
Can you see my
heights.
screen now?
Yeah, I can see.
So I have uploaded all data sets that you are going to be using until the end of the SPSS labs on here
Okay.
in this post. So if you go to Classroom, you'll be able to download this,
Classroom.
and then
Okay.
you'll be able to import the resident doctors data set.
Okay. Resident doctors data set. Okay. Okay. Okay.
Okay.
Okay. So okay.
Have you found it?
Yeah.
Okay, let me see if Ore is on the chat and she can help you through the chat box. So I'm just looking. I can see we have done just one example and we've almost spent 45 minutes. So I'll just go ahead, and if you are still having difficulties, you can draw my attention again, or you can type in the chat box and Ore will give you support. Is that okay?
Okay.
Okay. So another test that we do when comparing means is a paired sample t-test, and this is for paired samples. It's in the name. So for this particular example, we are looking at if there has been a change in the mean blood pressure between week 1 and week 2. So for this, we're using the Freetown SBP2 data set, SAV. So this an SPSS data set. So Freetown SBP2.SAV. I'll just double click on this and it will open in SPSS. So in this particular scenario, we don't have a test value because we are not testing it against a set value. We're just testing week 1 against week 2. We don't know if one is bigger than the other. So we come to analyze. We go to compare means again. And then in this case, we're going for a paired sample T test. So we have the first variable SBP1, the second variable SBP2. So just to give you some context, it doesn't really matter which one you put first. It's just that whichever one is bigger than the other, when you come to the mean difference in the output table, then it will either be positive or negative value, depending on which is bigger. So we leave everything else as is, and then we click OK. Is everyone at this point? Have you selected your variables 1 and 2?
You're moving too fast. So this new file, we have to get it from this new file you are talking about. We have to go back to that place to get it. Okay. SB2.
Have you found it?
Is it called Freetown SBP2? There are two of them,
SBP2.
SAV and Ditch. Oh, I don't know which one was supposed to.
It's SAV. It is here, Freetown SBP2.SAV.
Okay.
Has everyone found this data set? Anyone having difficulties finding the data set?
I haven't. I'm saying Freetown SBP_ditch.SAV.
No, that is a data set we are going to be using in the next example. So if you have downloaded your data sets from elsewhere, and you are not finding the data sets I'm talking about, they are all inside this zipped folder. So you can just quickly go to Classroom and download this, and then you see all the data sets I'm talking about.
Okay. So import data. Import data SAV. Okay. Import data SAV. There's no SAV in our option, so I'm seeing Excel CSV text data.
You don't need to import SAV. You just need to double click because SAV is already in SPSS format. So when you double click, it will open inside SPSS automatically.
Oh, okay. I should just double click the file. Okay.
Yes.
Oh, okay.
Oh, you can go to open.
Okay. Okay. It has opened. Okay. Okay. So I go to analyze, compare means,
Okay, so
paired
we're about
sample
to
t-test.
Yes, we're about to do that now.
Okay.
So we come to
sorry, excuse me, sir.
Yes.
I'm unable to download it. It's saying something went wrong. Like I will need to log into the OneDrive, something like that.
It's not a OneDrive link. What I shared was a zipped file. Let me see this.
Can I share my screen? I don't know. Maybe you can.
Okay. I'll allow 2 minutes for check-in.
Can I share my
screen? So who's
screen?
sharing her screen?
Me. Yeah, I want to share my screen.
Unachuku, okay. Ido,
Okay.
you have your hand up. Do you have a question?
No, mistake.
Okay.
So okay. So this is what I am seeing. I don't know whether.
Can you go to your
This is
Can you go
paired.
to your? I don't know if it's just me. I'm only seeing. Okay, I can see the output file now, but I'm not sure which data set you got this from. So can you go to the
Go
beginning?
back. Okay. Yeah, so
Yes.
this is the file that you said I should double click. These are the two of them.
Okay. So you have done the paired sample t-test.
Yes.
Okay.
So this
So
is
do
the
you want to
file.
interpret?
This is the this is the file that we are talking about.
Yes. It has the SBP1, which is the systolic blood pressure for week 1, and then SBP2, the systolic blood pressure for week 2.
Week 2. So this
Yes.
is it. So I don't know, should I redo it again so that you just see me and check, or?
Okay, go to analyze.
Okay. Paired. Okay. Then.
Am I the only one that cannot see what's going on the screen? Okay, I think there's a bit of lag.
Me too, I can't see.
Oh, you're not seeing?
It takes a long time between when you say you're doing something before we see it on the screen.
Oh, okay. Okay, let me just wait. Sorry.
So remove the variables from the variable box so that everyone sees how you selected the variables.
Okay, I should click this, right? Okay, let me click. Then I click this. Okay, so I click it again.
We still can't see. Well, I can't. I can still see.
What are you seeing now?
We can see that we have selected both variables.
Okay, I've removed them. Okay.
Okay, now select them. Okay, now select them.
Okay. And then the second one. Okay.
Okay, so you can click on OK. And then can you enlarge the output window?
Okay. Yeah. Okay.
Okay, so in your paired sample t-test, go up, down, sorry. In your paired sample statistics, you can see that the pair being compared are SBP1 and SBP2. It's giving you that statistic. And then it's also giving you the mean, standard deviation, and standard error for each week. For week 1, you can see it there. It's on the row that says SBP1. And for week 2, is on the row that says SBP2. For both, in both weeks. No, don't click anywhere else. Don't save it.
I should not save it. Okay.
Just hold on. So another important data point is that the N for week 1 and week 2 is the same. So this gives you some reasonable assurance that between week 1 and week 2, you have not lost anybody to follow up. It's still the same number of people that you assessed in week 1 that you're assessing in week 2, right? Okay. Because if there is a difference in the means and you are trying to understand why there is the difference, your mind will be going to a lot of different possibilities, and maybe a difference in the sample size between week 1 and week 2 might explain something. Who knows? But in this case, everything is very straightforward because the sample size has not changed. Now, in this paired sample correlations, it's just telling you that the blood pressures between week 1, the blood pressures in week 1 and blood pressures in week 2 are strongly correlated. If you remember, we said correlation can go from 0 to 1. 0 means no correlation. and the closer it is to 1, the stronger the correlation. And then the significance there is 0.000 ad infinitum. So it's telling you that it's very significant. Now, that's not our that's not what we're interested in here, but it just shows you that inside t-test there's a lot of information that you can actually get. Now, when you come to the table that says paired sample t-test, now it's telling you about paired differences because you are subtracting one from the other. And then SPSS is making it easy for you to understand by saying SBP1 minus SBP2. Can you see on the left of that table?
Okay.
Yes. So it means that whatever inferences you are making from this table is based on subtracting the mean of week 2 from the mean of week 1. So if you are getting a positive value, it means week 1 is greater than week 2. You can see it here on the table, SBP1 minus SBP2. If you have a positive value, it means the average BP from week 1 is greater than the average BP from week 2. Or in other words, on average, the blood pressure fell in that group of people, the blood pressure fell after 1 week.
Okay.
C'est comprend?
Yeah, so okay, yeah. Then also I don't know. Actually, I can save it now, right?
Don't run to saving. We are not done interpreting the table.
Oh, okay.
So when you go to the where is it now? Pierre's aha. No, don't move. No, just go back to the aha. So can we go down?
Down, okay.
Yep. Aha. So when you come here, paired differences. So when you go to the mean, so this mean 7.89 something, that's the average. That's the difference between the mean of week 1 and the mean of week 2. And it's a positive value. So based on what we said earlier, on average, the blood pressure went down by 7.89 points, 7.89 millimeters of mercury. Now, what is the standard deviation when you come to 95% confidence intervals? What's the confidence interval of that mean? You come to lower, you have 7.43. Upper, you have 8.34. So if you are using the confidence interval to interpret the significance, given that between the lower confidence interval and the upper confidence interval, there is no zero, what would be your conclusion?
Between the upper confidence interval, so which one is the upper one? The name is my arrow.
On your arrow, if you come to the paired, the part that says 95 confidence interval of the difference, no, not paired sample statistics, paired t-test, yeah.
Okay.
You can see that the lower is 7.4, the upper is 8.3.
Okay.
So given, yes, so it means your confidence interval is between 7.4 and 8.3.
Okay, so it is not bad now.
So what does it mean? Does anyone want to help?
Yes, I can.
Significantly.
Can help.
Yeah.
Humphrey.
Oh yes. So first
Okay,
of
Jerry.
all, I can
help?
answer. I can answer. Humphrey.
Okay,
Can you
answer.
hear me? Yes. What I can say is since our null hypothesis was that there was no difference, or the difference was 0, we're going to reject the null hypothesis and say that there is a significant difference on average of probably 7.89 with a 95% confidence interval of the upper limit being 7.4 and the lower limit being 7.4 and the upper limit being 8.3.
Okay. So you can also say, because remember, week 2 is less than week 1. So you can say that on average, the blood pressure fell by, reduced by 7.89 millimeters of mercury. And then the confidence interval is 7.4 to 8.3. But what you have said is correct. So, Unachuku, does that help? Have you understood what we have done? Abdurrahman?
Yeah. Oh yeah, I have a question. Like the other file, that other file that we did, the resident doctor. I don't know if you can walk me through that one, so that, because the first time that I was trying to ask you about it, I don't know if it's something that I can...
we can see if we can do that if we have time at the end. I'm happy that you've been able to go through this and you have understood the concept, so that we don't also deprive others of getting through the files. We don't actually have a lot of examples. Is that okay?
All right, okay.
Okay, Abdurrahman has a question.
Yes, sir. So I wanted to ask why the paired mean difference table, why there was no p-value, because it could have been
There
easier.
is a p-value. Let me show my screen. Where's the... Okay, so I've actually not even done the analysis on my own computer. Compare means, paired sample t-tests, SBP1, SBP2, and then okay. So you say there's no p-value?
Yeah, same here also.
Can you see it?
Yeah. Oh, wait.
So this significance is the p-value.
All right. Yeah. Thanks, sir.
All right.
Sorry, I have
Okay.
one quick question.
Do you have other questions? Yeah.
Yeah, one quick question. The correlation we are seeing under the paired sample table. Oh, the correlation we are seeing there.
Okay, Joe.
Is that?
Okay, is this Jerry?
Yes.
Yeah, please, just like I said, I don't see people's names, and I would like to, interact meaningfully. So just say your name before you ask the question, so that we can interact well. So your question about this, right?
Yeah, the correlation. Is it the usual correlation that we know, like the PSs and all that, that this is telling us that the data is like 98% correlated, like a positive correlation of like strong positive correlation?
Yeah.
Okay.
That's exactly what it's telling you, that these two readings, the readings from week 1 and the readings from week 2, are strongly positively correlated. At the risk of further confusing people, just a quick question. When you did t-tests and both the paired sample and the independent sample, when you did these things in the main class, were you told about the assumptions for t-tests?
No.
Okay. So this would bring us back a bit. But anyways, in order for you to do a t-test, right, whether paired sample or independent sample, or even the ANOVA that we're going to do next, there are a number of assumptions that you are working with. So I went ahead and demonstrated the t-test without checking those assumptions, because what we're just trying to do is to demonstrate how to do the t-test. However, there is an assumption that your data is normally distributed, and then if you are doing a paired sample t-test, for example, that the variances are the same. Sorry? Someone said something. Did you want me to repeat what I said?
Okay, I think they just left their mic unmuted.
Yeah, they left their mic unmuted. So in all of this, we are assuming that our assumptions are that the data are normally distributed. And then for the paired sample, we are also assuming that the variances are equal. It's a very weird word that you only hear in statistics. Homoscedasticity. Basically, you are assuming that what's it called? The data are normally distributed and that the variances are equal. So when we get to regression, but down the line, we're going to demonstrate to you how to check these assumptions: equal variances and equal and normal distribution and all the other assumptions, because those regression and other things also have these checks in place. Okay, so just keep that in mind, that these tests, these parametric tests, they're called parametric tests because your data obeys certain parameters: normal distribution, equal variances, and a host of others. So if your data does not obey that, then there are non-parametric tests that you can also do. Just like when your data is not normally distributed, you don't calculate mean, you calculate median. So if you have calculated median, do you go ahead and do a t-test? You can, and SPSS will give you results, but your results will not give you the true picture. So do we understand independent, the first one and the second one? We understand the t-tests so far?
Fantastic.
Okay. So we have interpreted the findings from this paired t-tests when Unachukwu shared her screen. So we have done now a one sample t-test. Where is it? We have done a one sample t-test. We have done a paired sample t-test. Now we are going to do an independent sample t-test. So this independent sample, you are looking at two different groups. You are looking at people who are treated and people who are not treated, like in a clinical trial. Maybe these are the treatment group and this is the placebo group. Or maybe in a cohort study, you are looking at smokers versus non-smokers, or people who, I don't know, exercise versus people who do not exercise. Does that make sense? So these are two different groups of people. In the paired sample, it is the same group of people that you are testing at different time points. Two sets of observation, the same, from the same sample. Here, where is it going? Yeah, here you have independent samples. So this, the mean from the treated does not depend on this, neither does this depend on that. They are completely different sets of data. Does that make sense?
Yes,
so
please.
Okay. So I'll just keep on going until someone interjects and says, I need to slow down or repeat myself.
So in this case, before you go on,
yeah.
Can we
Please
safely,
state it again.
can we safely say that?
Okay.
Can we safely say that for the paired t-test, it's the changing factor there is time or points, like different points, like the same group but at different points in time. That's the criteria.
It may not always be time, but yes, it's the same variable measured. It's usually the same variable measured at different points in time, like before and after studies, before intervention, after intervention, in the same set of people. But so that is so the sample themselves, the people in that data set have not changed. It's the observation that is at different points in time, compared to in the independent sample t-test, where you have an observation that has been taken roughly at the same time, but across two different groups. Does that make sense? I don't know who asked the question. Okay, silence means yes. Right. So for this one, we're going to be using a different data set, Freetown SBP _ dichotomous ditch. So everyone find this data set and open it. I'm going to my own folder now. So SBP2 ditch. So I just double click and voila. That is the data set. So the good thing about SPSS is on the top here, it will always tell you which data set. It will always tell you the name of the data set you are using. That way, you don't accidentally do the wrong analysis on a different data set. So if we look here, it is asking us to do some things. It's asking us to use systolic blood pressure as the test variable. And then
your screen is not showing though.
Can you see my screen now?
Yes.
Okay. So you can see the instructions here are we're still going to do the same analyze, compare means, and we'll select independent sample T test. So let's go to SPSS. There's systolic blood pressure, DICH. So we come to, can you see my data sets? You can see my data view. Okay. So analyze, we come to compare means, and then we come to independent samples t-test. Right? So what is our test variable? We are testing systolic blood pressure. What is the grouping variable? The grouping variable is treatment. Were you treated or were you not treated? Now, the grouping variable is supposed to be a categorical variable. If you look here, this is continuous. So we come to the, can everyone see what I'm doing?
Yes, you can see.
No, I can't see.
Can you see my variable view? My data view rather?
Yes, we are seeing your data view.
Okay, so I'm going to the variable view now because, like you can see, treatment here shows that it is a continuous variable. However, we are grouping our, our data is grouped into two categories, treated versus not treated, right? We are looking at the difference between people who have been treated and people who have not been treated. So this is the variable number 5. So I'm coming to here where it says measure, and I'm going to change it into nominal because there is no hierarchy between whether you have been treated or not. We're assuming there's no hierarchy. There's just two different groups, the treatment group versus the non-treatment group. Then, because they have values of 0 and 1, it's just 0 for not treated and 1 for treated. We don't need decimal points, so I'm going to remove these decimal points. So it's going to be 0 decimal points, right? And then label, I can even come here and assign label. Sorry. So why is it this is it inputs? Trying to assign a label,
Values,
but
the value side, the values.
Oh, values, not label, sorry. So when you assign value, 0 is not treated, right? And 1 is treated. This is all a bit extra, but with just this that I've done now, when we go back to the data view, we can now see that treatment, it doesn't have a what's it called? It doesn't have a decimal point. And then when we come to this, if we want to see variable value labels, we can now see that this is not treated. And then when we go down, we can see these ones are treated, and it just makes it a bit easier to understand the data set, even though in the real sense on the back end, it's just zeros and ones. And also on your output table, because I have now added a value label, then on the output table, when we do our analysis, it's going to say treated, not treated. It's easier to interpret that way, because if you are doing several analyses and everything is 0 and 1, it's very easy to get mixed up what is 0 and what is 1, and you go and report that in your paper, and you know, you get a lot of questions from reviewer 2. So let's go to analyze. Compare means, independent samples t-tests. So now our test variable is the systolic blood pressure. Our grouping variable is the treatment. So treatment status, treated or not treated, and then we put it in here. So we still have to define groups, right? So group 1 is 0, and group 2 is 1. Remember, we used zeros. Our data sets, sorry, our data set uses 0 and 1. So if we leave it here as 1 and 2, it will not give us the output we are looking for. Are we good so far?
No.
Okay.
I'm not good.
No. Okay.
I'm not good. Yeah.
Where did I lose you?
The frequent changing of those data, like back, is beginning to confuse me now. I don't know, because like when I reach this part,
so
I try to put,
yes.
no, I don't know what to do again, unless maybe I share my screen. I'm becoming confused.
No, don't share your screen. Where did you stop? Where did you understand to the point where we selected that we are testing systolic blood pressure?
Yes, I put my distance. So right now I put use specified values, group 1, 0, and 1. Then later you started changing some things in the
No, I didn't change. Okay, in the data and variable view. Okay.
Yeah,
so
you started some things.
Here, the only reason why I changed this is so that I can go back and undo the changes, right? It's not difficult. So I will undo the change. I will do the analysis with the changes and without the changes. The only difference there is that on the analysis output, one will show 0 and 1, and the other one will show treated versus non-treated. So let's if that is the only let's go. If that's the only query you have, this treatment variable, you said you have done the grouping of 0 and 1. You have done this.
Yes.
Okay. So that means we're on the same page. We're at the same place. Okay.
Okay.
So now we click on OK. So where I have on this group statistics, where I have not treated, on your table, you are going to have 0.
Okay.
And where I have treated, on your table, you have 1.
Okay.
Does that make sense?
Mm-hmm.
Is that what you have?
That's what I'm trying to look at. Group statistics.
Group statistics.
Statistics. Okay, let me look for it. Group statistics, 300, 300.
While she's looking for it.
Yes, your question. Or
Yes,
we just go
while she's
ahead and
looking-
interpret this, right?
Before you interpret, I got a little confused. When selecting the variable of interest, you selected just one variable.
Yes.
But I thought that we are looking at 2 systolic blood pressure. Oh, okay, sorry. It's just one after those that were treated and those that were not treated. Sorry. It's just one variable, but grouped.
Yes.
Okay, I've gotten it. Yeah, I found it. Group statistics.
You have 0 here. You have 1 here.
Yeah, 0 and 1.
Okay. Okay. So all that changes, all those changes I was making on the back end, is something that should have been demonstrated during the intros to SPSS lab, your first SPSS lab. So on your variable view, where is it here? On the variable view, this treatment variable, instead of just leaving it like that, I came here and I assigned values. So wherever SPSS sees 0 for only this variable, wherever SPSS sees 0, it will write not treated. Wherever it sees 1, it will write treated.
Okay.
Does that make sense?
Yeah, okay.
Okay.
Sorry, one more question. This label under your variable view, what is it is it for?
The label, so the variable names, there's a naming convention, right? Let's say, usually here you would not, SPSS will not allow you to give space, for example. It will not, if I say I want to write SBP, if here I want to create a new variable and I say SBP morning, you see, it's telling me it's an illegal character. Basically, the space is an illegal character. So usually there is something called snake case. This veering way off topic now. So SBP underscore morning, it will allow me to create that variable because I have not left any spaces. Let me just delete it again. So this label here gives me the chance to explain the meaning of the variable. Sometimes what you write here, the variable name might not be very clear to whoever is reading your data set. Remember, sometimes you are going to be collaborating. So this SBP morning now, I might just say, okay, systolic blood pressure measured in the morning. So that's this is just an explanation of what is here. That's the use of the label. Does that make sense?
Fantastic.
Okay. All right. Let's where is it? So let's interpret our t-test now. Our paired, our independent sampled t-test. On the group statistics, we can see that there are 300 participants who have not been treated. At the same time, there are 300 participants who have been treated. The mean blood pressure among those who were not treated is 159. And the mean blood pressure for those who were treated is 121. Systolic is 121 millimeters of mercury. No issues so far?
Yeah, 159, 121, yeah.
Okay.
That's what I got. Mm.
So we come to the independent samples t-test. This is the table where we interpret our t-test. Now, remember I said that in your assumptions for t-test, there is normal distribution. I did not draw histograms for either of these. I'm assuming the distribution is normal. Okay. Then the second assumption was that the variances between the two groups are equal. Now, with equal variances assumed, sorry, can you say that again?
We can't see your screen. I can't see your screen.
Can anyone else not see my screen?
I can see your screen. I have a question. When I was doing my own, I couldn't find the place I'm saying independent samples effect sizes. I didn't see it in my own. I don't know why.
There's a small box to tick when you are selecting your variables. If you tick display effect sizes, it will display this table.
Mm. Where is the small box? I don't know if you can just show us.
I think it's not present in your SPSS 25. It is present in SPSS 27 and above.
Okay,
Yeah.
okay.
It may be in another, it may be somewhere else. Maybe somewhere else in your own. Maybe under options. If it's not here, it might be under options.
Options,
To estimate
okay.
effect sizes. Yeah. So like I said, those effect sizes, they have some merit when it comes to also determining whether the difference that you have detected is clinically significant and all that. But my grasp of it is not too strong to be able to explain it to you. So if you have questions about effect sizes, you can direct them to Dr. Abioye or Dr. Ebua. They'll be able to give you more details on that. So this is the table, the output table for the independent sample t-test, right? We have assumed that the variances are equal. Now we come to, this is the test that does test for equality of variances. In this table where you see F test, that's the Levin's test. Only for this one of the rare cases where you want to see that your p-value is not significant. Does it make sense? It doesn't make sense. But for your for your test of equality of variances, you want the p-value to be not significant. So if the p-value is not significant, it tells you that the variances between your two groups that you are testing is equal.
Okay.
Okay? Yeah. Because your null hypothesis says that the variances are equal. Your p-value being greater than 0.05 means that you cannot reject that null hypothesis. Therefore, your variances are equal.
Wait, your variances are equal, so you cannot reject the null hypothesis.
you cannot reject the null hypothesis for the test of equality of variances, not for what you are testing. That's why don't think too hard about it. Just check whenever you come to test of equality of variances, just check to see that your P value is not significant, then you are good to go.
Okay.
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 So we come to our T test proper. The T statistic for this test is 23.3. Like I said, I'm not giving too much weight to that. Let's come to the mean difference. So the mean difference in systolic blood pressure between those who were not treated and those who were treated is 37.89 millimeters of mercury. Is that I don't know, does anyone else think this is amazing, even though it's a hypothetical data set? Does anyone think apart from me think that this is amazing? You are treating someone with a very high blood pressure, and then in the group that you treated, the mean difference between the group that were not treated and those who were treated, meaning this is not treated minus treated, right? That's what this is telling you. Not treated minus treated is what the mean difference is telling you. So it's saying that on average, the intervention, whatever the intervention is, led to a 37.89 difference in systolic blood pressure between the two groups. And mind you, we have already, during our study design, we have already made sure that the group who are treated and the group who are not treated are as similar as possible, because we took a random sample, we did randomization, we did all that stuff, we did masking, we did not allow people to select their friends to the treatment group while putting their enemies in the non-treated group. We did all of this. So it means that if everything in the study design is good, then your intervention has brought about this amount of drop in blood pressure, in systolic blood pressure. Now we are coming to the significance, two-tailed significance, much less than 0.01. So this is a statistically significant difference. Now, but let's play devil's advocate and say that even that this 0.01, let's say the p-value was 0.5 or 1 or 2, meaning statistically it is not significant. But the blood pressure difference is almost 40. And in other studies about blood pressure, we know that even maybe 5 or 10 millimeters of mercury drop in blood pressure can give you a huge advantage when it comes to other outcomes like stroke, like other things that are associated with blood pressure. So when you are reporting your findings in the journal, your interpretation and your discussion would also highlight this fact. I'm just kind of emphasizing this because there are many times when you do your stats and you see that it's not statistically significant. So does that mean you throw away the results? No. Sometimes it's not statistically significant, but clinically it's significant. Sometimes what you will be looking at here is not even mean difference in the systolic or diastolic blood pressure, but you are looking at mean difference in the number of deaths. So at any given point in time, number of deaths, a reduction in deaths is a very clinically significant figure, especially maybe you are talking about infant mortality, maternal mortality, So just to re-emphasize, I'm sure it has been spoken about in class that we should not always depend only on statistical significance when we are interpreting our results, when we are discussing our results. So we said our p-value is less than 0.05, statistically significant. We come to confidence interval also is between 34 and 41. It does not contain 0, also statistically significant. I'm quiet because I'm waiting for questions.
You said our p-value is less than 0.
Sorry, one at a time.
Yeah, sorry, you said that our p-value is less than 0.05. Then you now said our variances are equal, so we cannot reject the null hypothesis, and that means our p-value is more than 0.05.
No. There are two p-values going on in this table. There are two null hypotheses going on in this table. And in order to avoid that confusion, that was why I said in summary, when you are interpreting your equality of variances assumption, just come here, this Levin's test, just check to see that the p-value for Levin's test is not significant. So this p-value here is for the test of equality of variances, not for the t-test. However, the t-test depends on the equality of variances. If your variances are not equal, then you shouldn't be doing a t-test. Does that make sense? Yeah. So this just that's the use of this Levin's test. It's not for the overall hypothesis of difference between systolic and between treated and not treated groups. That one is here under the t-test, and that's why it's been demarcated, even though very poorly.
That is the root significance two-tailed. That's the p-value. Okay.
This is the p-value for the t-test.
Okay.
Is anyone else confused, or are we all good to go?
I just have a problem. It's Humphrey. I have a problem with the data set.
Okay.
The 300 observations are treated, 300 are not treated. If you would ultimately alternate the same, it will still give the same result. So is that a problem?
It will give the same results, but you have a negative value. Your mean will have a negative value.
All right, which I have.
That's what you are seeing, right?
I have calculated, but it looks still the same.
Let me stop sharing, and you can share your screen. Sharon, your hand is up. What's your question? Sharon Ajudwa?
Sorry, that was a mistake. So sorry.
Okay, no problem. Who was it? Humphrey that had a question? Can you share your screen? Otherwise, we go to Anova. We have less than 20 minutes now.
Sorry, while he's sharing his screen, sir.
Yep.
When we are reporting this data in a case where our p-value is telling us that it's not statistically significant, how confident now will we be in saying that that medication actually resulted in that drop and not some co-founder or something that maybe we may not have accounted for, maybe a fasting period, maybe the majority of those that were treated were or something like that.
Yeah, so that is the reason why you still won't throw away your results. You would discuss that in your discussion section. You would say that maybe the reason why your results are not statistically significant, it might be due to your sample size. It might have to do with the fact that in your study design, you might have not considered some other factors. And then maybe you might need to do a bit more in-depth analysis on that. You know, I told you further down the line in these labs, we are going to do regression and all that. So you might need to do something more in-depth in order to see where the issue is. But even if you do all those things, and another thing is you might also recommend that other scientists might need to repeat it while considering some other factors, or while increasing sample size, or while ensuring that their study is powered. So from your limitations, you try to see which of the limitations led to maybe a non-significant result. There's a lot of meat to discuss there. Yeah.
Thank you.
Humphrey, yeah.
Very clear.
So not treated versus treated, yeah. Treated versus not treated. Okay, so you said you are getting the same.
I'm getting the same result because here from the output you can see not treated the first one, the average, and then I alternated and I got the same. So that's why
this is not treated. So the mean in those who are not treated is higher. The average for those who are not treated is higher than the average for those who were treated. So you have a positive value of your mean difference in mean, right?
Yes.
So you said you flipped it. Okay, can we go down? Let's see.
I flipped it. This is it's
yes, now it changed.
Because you didn't change, you only changed the value labels. If you look up there on your table, it's now saying that treated is greater than not treated.
Yes.
So you didn't flip anything. You only changed the value labels. But if on your
no, this is the one that is not treated and then treated. This is the initial one.
I understand.
Yeah. When I flipped it, it's the result is still the same.
But you only flipped it in your variable view. You went to the variable and changed it. Yes. Yeah, that's what you did. But you still on your output table, it still shows that it is subtracting the bigger one from the smaller one. So you will not get a negative sign. If you check your group statistics.
Okay.
Yeah.
It's okay. So it's okay.
Yeah.
But then I was for the fact that we do not reject the assumption that the equal variances are
no. Even there's this very weird thing about statisticians. They'll tell you the variances are equal or the means are equal. When you put them side by side and you're just using your eyes to look at them, they are clearly not equal. But that's why we're doing this whole statistical tests. We're checking to see whether that difference, let's say in this case, between 159 and 121, is that difference statistically significant? And from our t-test, it is yes. But you can have a difference and it is not statistically significant. Then in your interpretation, you say that you don't have sufficient evidence to reject the null hypothesis. So that's what it is. It's not really saying that it is not different, but it's telling you that before you reject that null hypothesis, go and look for more evidence. That's the essence of the statistical test.
That's perfect. Thank you.
Yeah. Okay. Can I have the screen back? Okay. So we have spent some time. We have interpreted this table. So basically, what it's telling us is that the intervention works and it brings down your BP by around 37.89 millimeter of mercury. Okay, it has cut here. Let me give you where's this thing? Not this. Where's the output table? So it's telling us that this is the average amount by which people see a BP reduction. However, it can be between 34.6 and 41.1. And Then we now go to practice. So this practice one, because of time, I would encourage you to do yourself. Sorry?
We can't see your screen. We can't see your screen.
So is it just you or? Okay, okay.
Yes, Jerry, I'm also not seeing your screen, sir.
Okay. Now can you see?
Yes, I can see
it.
Please.
Okay, so I was just interpreting the paired sample t-test, and we said that this is the mean difference, this is the average difference between those who are treated and those who are not treated. So on average, those who are treated had an average BP that was 37 or let's say 38 millimeter of mercury lower than those who did not receive the treatment. And this is the confidence interval. So when we come to the next page, this is like I was saying, this is a practice test. However, we have 15 minutes to go on this on this lab. So I'm going to leave this for you. You can take the ion trial data set and answer this question. A clinical trial has randomly assigned 1,500 pregnant women to daily ion supplementation or placebo to assess whether supplementation increases hemoglobin by the time of delivery. So only 982 women were identified at the time of delivery. That means some of them fell off from the follow-up. Others either had a spontaneous abortion or did not return to the designated hospital for delivery. You are given a data of the hemoglobin concentration at the time of delivery, and you are asked to compare the average of hemoglobin in those who received ion versus placebo. So you lost almost 600 participants to follow up out of 1,500. So the question is for you to check between the people who received ion and those who did not receive ion. Check to see if the hemoglobin increased at the time of delivery. So just like we did systolic BP 1 and 2, you are going to use variables from that data set to compare. So this is for practice. I'm not going to demonstrate that. So ANOVA is analysis of variances. This is what you do when you're comparing means in more than two groups. So more than two independent groups. When your independent groups are two, we do an independent sample t-test. So we are going to use the same data set, Freetown SBP DICH. So I'm just going to open that data set. So we are going to do an ANOVA to basically, sorry, this keeps happening. We need to edit this. This assignment instruction. So just bear with me.
Okay, this is Humphrey. While at it, I just wanted to ask from the data set that we are going to do to conduct the assignment.
Yes.
Is one treated? Is one given the intervention and 0 not given the intervention?
Yes, for your data set, yes, it's 0 and 1, just like this one.
So 1 is given the intervention, 0 is not given.
Yes.
Okay,
so let me just check I think we're supposed to use this BP trial data set for the ANOVA. I'm just opening it to explore the data set to see if we have 3 independent groups. So placebo, drug Y, and drug X. Yes. So ignore this these instructions. We are going to edit them and provide correct instructions. So let's open this data set, BP trial. Let's import this BP trial data set.
We're not using free SV data again.
No, we're not using Freetown because that has only 2 groups. The BP trial data set has 3 groups, and we want to do a new one. Yeah.
Okay.
So BP trial open.
CSV.
Okay.
So it's a data file, right?
Okay.
It's a data file, right?
So now it has opened.
Sorry, is it a data file?
No, it's where is it?
Because I don't have that.
It's a CSV. It's a CSV.
Is it in the classroom? I don't have that file.
Yes, at the beginning of our class, I uploaded a folder because some people did not have some of the data sets. So I uploaded all the data sets that we are going to be using for this these SPSS labs, including the ones from subsequent classes. So if you go to what I uploaded at 5:40, you'd find among that folder, you'll find the BP trial data set.
5:40. Sorry.
Yes. Ojo.
Am I looking at under data sets?
No, it's just an announcement. I just made an announcement at just at 17:40, and so under this tab stream, you see SPSS data sets, and you see the folder, the zipped folder. Alfred, you have a question?
Yeah, Yisa, thank you. I'm trying to import the CSV file. It's placing all the data in a single column.
Okay, so if it does that sometimes if you don't select some. So when you are importing, you select that you are trying to import CSV data. You select your CSV. You say open. So if you are not using the same version of SPSS as me, there might be some different options to choose. But one thing is to select that the first line contains variable names, because it does in the case of this data set. And then the delimiter for this data set is comma. CSV means comma separated value. So you can see this SBP treatment, you can see they're all separated by commas. So if you specify that the comma is the delimiter, it will separate these things into 3 columns. And then when you click OK, you should see the data set the way I also see it here.
Sorry, please. You're moving fast. That column again, can you go back? The place you were talking about column.
Have you been able to import the data set?
Yeah, I've imported it. So, but that place you're talking about column something, like there's somewhere you were. Can you go back to that place? There's
okay,
that file.
So I said import CSV data, BP trial.
Okay, we have done that.
So if sometimes you just say open and click OK, and it will appear the way it's supposed to appear. Sometimes it will not, because you have not selected some options. In the case of this data set, the first line is the name of the variable. So you click this to say the first line is the name of the variable. In addition, we are using comma to separate the columns from each other. SBP, or everything on the left here, is systolic blood pressure. Everything in the middle here is the treatment. That's the treatment in the value label. Everything here is 0, 1, 2. So we are using comma to separate each column, and that's why we said
Okay.
comma. And
Okay.
once we click OK, everything will appear the way it's supposed to.
Okay.
Okay, so have most of us been able to import our data sets?
Well, I could not even download it. If I click on the link, it doesn't allow me to open it.
Okay, but so not to worry, because we are short on time, and to also remind you that this session is being recorded, so you'll be able to follow the processes that all the steps that I'm conducting now. Try and follow our explanation and the discussion and what the ANOVA means. So, like I said, ANOVA is when we are comparing means across 3 groups, or rather more than 2 groups. We're comparing mean across more than 2 groups, which are independent of each other. So the commonest ANOVA, which is what we are going to do today, is the one-way ANOVA, and it also has similar assumptions to the t-test, which means that we are assuming this variable, this systolic blood pressure that we are comparing across the different interventions, placebo, drug X, and drug Y, is normally distributed. We are also assuming that the systolic blood pressure, the variance in systolic blood pressure is the same among the placebo group and the drug X and drug Y groups. And that's those are the assumptions. So if these assumptions are satisfied, we can do ANOVA. So
I have a question.
Yes.
Just another question. What if you have, for example, outliers in your data set? Is it still falling under the assumptions?
You have outliers and your data is not normally distributed, or
maybe it's normally distributed, but you have outliers. For example, we have in this data set 60, a few 60s from the systolic BP.
Yes. So for this data set, for all the data sets we are using, I have not checked whether they are normally distributed. I'm just demonstrating how to do ANOVA and how to do t-test and how to do independent sample t-test. Because like you said, some of these data sets might have outliers. So if they have outliers and they are skewed, there are other set of tests that you do. They are called non-parametric tests. I was hoping that we'll be able to move fast enough in this class so that I'll be able to demonstrate the non-parametric counterparts. So for the one sample t-test, there is a non-parametric counterpart to it, which is Wilcoxon negative sign test. And there is a paired version of that for the paired sample t-test. There is, I think, is the McNemar test for the independent sample t-test. There's Kruskal-Wallis for ANOVA. So these are things that maybe in one of the subsequent classes, we can mention their names because the interpretation is basically the same. So if we mention the names of those tests, you know that, okay, when you come to analyze, you are not checking for means now, you are checking for non-parametric tests because your data is not normally distributed. Does that make sense?
Yes, thank you.
Okay. So now we are checking between, this treatment variable. We are checking between 0, 1, and 2, right? Let me see. It has 0, 1, and 2. 0 is placebo, 1 is drug Y, 2 is drug X. So this is this is like a proxy that the person who designed this data set did. What we did earlier with the treated and not treated here by manipulating the variable is what the person should have done, but maybe the person was not sure how to do it. So 0 is placebo, not treated, right? Placebo. 1 is, was that drug Y? And then
yes, it's drug Y.
2 is drug X. Like I said, we can leave it as 0, 1, 2. It's just that when you come to your output, you are going to see 0, 1, 2. And I personally don't like seeing that. I like to know what I am looking at. So we come to analyze, we come to compare means, we come to one-way ANOVA. Analyze, compare means, one-way ANOVA. So we click. Now, what is our dependent variable? It says dependent. So basically, the dependent is that continuous variable that you are trying to compare across the different groups for the purpose of ANOVA. Right? Then treatment, the factor is the what's it called?
Independent variable.
No, the factor is basically independent. It's basically the categories that you are dividing that variable into. So the factor here is whether they are treated. The arms of the trial is the factor. So the placebo arm, the drug X, drug Y. So that is the factor here. So that is that's what we are doing. So we click OK, and by magic we should have our ANOVA. Now you will see that this ANOVA output is very basic, and given that we did an independent sample t-test just now and it was giving us tons of tables, you might feel a bit underwhelmed. Like, why are we having just these very few what's it called? Just very few outputs. Don't worry, we'll go back after doing this. We'll go back and test further. So now ANOVA is telling you that there's something called between groups and then the within groups. So between the groups, difference. Is there a difference between placebo, drug X, and drug Y? Or are they the same? So this is what between groups is asking. Is the mean blood pressure, is it the same for group X, group Y, and placebo? So this one-way ANOVA is telling you that it is not the same because the difference between them is statistically significant, right? But now, that is not telling me anything. So there is a difference. Does that tell me that the placebo group is less than the drug X group, or drug X is having an average BP of less than the drug Y group? Where is the difference? It's not telling you that. So in order to explore this further and detect where the difference actually lies, is it between group 1 and group 2 or group 3 and group 4, you need to do something called a post hoc test. And we're going to go back and do it. So let's go back to our data view. Is this BP trial? Yes, this is BP trial, right? Is it? Placebo. Yeah, this is BP trial. So we come back to analyze. We come back to compare means. We come back to one-way ANOVA. We leave everything here unchanged. And then we come here and click on post hoc. So these are all the different types of post hoc tests. For each of these things, these are names of people or that discovered the test and all that. Don't ask me what's the difference between Bonferroni and Skefe and all that. For the purpose of this test, of this course, the designers of the course have determined that the Bonferroni conversion is more appropriate. Okay, some courses, some people, these are the two more common ones. Again, I'm not a statistician. I don't understand. I don't know what's the difference between when you do a Skefe test versus a Bonferroni test to check the differences between the groups. I know that you end up getting the same outcome. It will tell you where the difference lies, and that's the important thing. So for this particular course, we're going to stick with the Bonferroni post hoc test. And you can see inside this box where this is the box where all the post hoc tests that assume equal variances, this is where they all come to play. Can we see?
Yeah, please, I have a question. This post hoc test, are we using it for the same data of is it
Yes.
for this
For the same ANOVA. For the same ANOVA.
For BP trial?
Yes, for BP trial. The only difference, the only thing is that, you know, when we did the ANOVA in the first time, we saw that there's a difference between the groups, but we don't know which group is different from which.
Okay.
So that is what Bonferroni is about to tell us now.
Okay, so we have to redo the test and add.
Yes. Now we have. Yes. Now we have done it with the Bonferroni test. Now you can see this is the ANOVA. This is the initial ANOVA that we did. This is the difference between the groups. There is a significant difference between the groups. Where does the difference lie?
Bonferroni and Skefe, or just Bonferroni?
Just Bonferroni. So in my school where I did my postgrad, they told us to do Skefe. For the designers of this course, our course directors, they prefer Bonferroni. So sometimes it's a matter of preference, depending on how you understand the depth of all the calculations that are going on in the back end. So I have not studied statistics to that depth. So I'm just trusting the course directors that Bonferroni is a good test to do as a post hoc.
Okay.
Okay. So if you look at it here now, if we look at this multiple comparison table, we can see that on this first line, we are comparing the placebo to drug Y and drug X. What that means is that you are subtracting the mean systolic blood pressure of people who took drug Y from placebo on this row. So that is the mean difference. So on average, drug Y, those in the drug Y arm had a 37.8 millimeter of mercury less BP than those who took placebo. And drug X, those in the drug X arm had 47.5 millimeters of mercury less blood pressure compared to those who took placebo. So that means that for both drug Y and drug X.
Sorry, my own is not showing drug X and Y. It's showing treatment 0 and 1, treatment 1 and 2.
It's showing 0, 1. Yes, 0, 1, and 2, right?
Yeah.
Because you did not change it here in the variable view. I told you, for me, I like to know what I'm looking at. I like to know that 0 is placebo, 1 is Y, and 2 is X. So if you come here and define the value labels, your output will show you what the value labels are.
Okay.
So here you can see now that the drug Y has the drug Y participants had less, their BP was less than that of drug placebo by 37.8. How do we know it is less? We know that placebo is on the left here, and we are subtracting Y and drug X from it, and it's carrying a positive sign. There's no negative sign. That is how we know that drug Y users had lower BP, and drug X users also had lower BP. So and then we now go ahead and also look at the p-values, and we can see that, okay, the difference in systolic BP between the drug Y users and placebo is significant. And it's the same thing for drug X versus placebo. It's also significant. So our post hoc test has given us much deeper insight than we could have hoped to gain by just doing a one-way ANOVA. So we can now comfortably make inferences from this table when we are reporting it in our results. Would say that, okay, on average, the people in the drug, we can manipulate the English however we want. We can say that both treatment arms of the trial saw a significantly lower systolic blood pressure than when compared to placebo. For drug Y, the mean blood pressure was 37.8 millimeters of mercury less than placebo. These are the confidence intervals. And for drug X, it was 47.5 millimeters of mercury less than placebo. These are the confidence intervals. Of course, it makes sense because you are comparing, it's a clinical trial, you are comparing what happens when you do something compared to placebo. Maybe drug Y is your current treatment, drug X is your new medication. So if you want to compare drug X and drug Y also, you come to this place, right? And you look at drug X, and if you subtract drug X from drug Y, and if you subtract drug Y rather from drug X, you have a negative value. So that means the systolic blood pressure in those who received drug Y was actually higher than those who received drug X. Or on the flip side, you will say that drug X actually led to a greater fall in systolic blood pressure compared to drug Y. Questions?
Sorry, one question.
Yes.
Where you have within groups,
Mm-hmm.
the mean, the sum of squares.
Yes.
Is it the means? Is it the sum of squares you are looking at, or the mean square now?
So in this
what does it
ANOVA,
mean?
we are looking at the significance.
Okay.
This sum of squares and all that. These are things that these are statistics that get calculated when you are calculating the ANOVA. Let's say you are calculating ANOVA by hand between the groups or within the groups. It will bring out these values. But then again, what we are mostly interested in is whether in between group A, group B, and group C, if there's a difference at all. And this is where you find the difference on the column where it says significance, because you are checking the p-value to see if there's any difference between the placebo versus drug X versus drug Y. So once you detect that there is a difference and you want to explore further, then you do the post hoc, which was the Bonferroni test that we selected when we were doing our ANOVA, and then it will give you this.
Oh, okay, that is understood. So just to reiterate, whenever we are checking for variance between groups and our p-value is greater than 0.05, it means that
less than.
when it's less than 0.05, it means that there is variance. If it is greater than, it means that they are equal.
It means, yeah, the second part of your statement is correct. I don't want you to use the word variance because variance also refers to a particular thing in statistics.
Equal variance.
Yes.
Equal.
Yeah. So when the p-value is less, it means that the mean blood pressure between these three groups are not the same. So they are not the same, but which one is bigger than which? You know, is the difference between placebo and drug Y, or is it between placebo and drug X, or is it between drug X and drug Y? That's why we did the Bonferroni test. And then it has told us that actually the three groups are completely different from each other. If you look at this table.
Yes.
That's good?
Yes, sir, that's good.
Okay. So let me come back to the slides. Again, you know, this, sorry about this. I will feed this back so that the slide can be corrected and we'll use the right data set. How have we seen today's class? Are we leaving this class in a better place compared to when we started, when it comes to doing one sample t-test, a paired sample t-test, independent sample t-test, and an ANOVA using SPSS? Can we confidently do this in our day-to-day projects?
Fantastically, on my end.
Okay. Onachuku, I've not heard from you. Can you do it now?
Yeah, I was asking you to show me the beginning part. That one I was telling you about that I didn't understand when I couldn't import the data. That
one
the
sample.
beginning part. Yeah, that beginning part, the one sample from resident doctors. Because I was telling you that time.
Okay, no problem. We are at the end of the class now. For anyone who does not, I'm just going to recap the one sample t-test. You don't need to stay on. The class has ended. So
let me share my screen. Let me just share my screen so that
you can share your screen. Yeah.
Okay.
So for anyone who is interested in seeing that, that's fine, but the class has ended.
Thank you. Let me share my screen. Allow. Okay. So I have to import the data. Import data. And then doctor is C is CSV. Okay. So that's CSV. CSV. Open. Okay. Okay. So this is a resident doctor distance.
That's the resident doctor's data set. And if you remember, the question is asking you, is the mean age of these resident doctors significantly different from 30?
Okay.
So you have only one sample and you are checking it against a test value. So you do a one sample t-test.
T-test, okay. So age.
Age is your test variable. Your test value is 30.
Okay.
And then you click OK.
Okay.
Now go to the very bottom. Yes, one sample statistics.
Okay.
So this has the one sample statistics shows you the mean and standard deviation and the number of observations that were considered from within this data set. So 161 there tells you that 161 variables within your 161 observations within your data set have been considered for this calculation. It doesn't
Okay.
mean there are 161 resident doctors in your data set. If there are some, so you are the one that knows how many people you recruited in your study and how many people are in your data set. If you are expecting 170 and you are seeing 161 here, it means that there's something wrong with some of the observations in your data set and you need to do some data cleaning. So that's just by the way. So you can see the mean, the standard deviation, and standard error. Now, when you come to one sample t-test, you see that the test value you used is 30.
Okay.
You can see that the variable you are considering is age. You can see it there. And that the mean difference is 4.12. So it means that the test value was subtracted. The test value was subtracted from your sample mean.
Okay.
And that's why you're having 4.12 is a positive number.
Okay.
And then when you look at the significance, it's 0.00000.
So which means it's statistically significant.
It's statistically significant. So it means that your sample mean, the mean age of your resident doctors is not 30. It's not the same as 30. So on average, they are 4 years older than 30 with confidence interval of 3.4 to 4.9. Does that make sense?
Yeah, I get it now. Thank you.
All right, everyone, have a nice weekend, or rather have a nice week ahead, and see you in our next class.
Thank you so much.